Hello and welcome back to the Energy Onion, Energy Systems Engineering Training Certification, Chapter 8. With introduction, lighting, HVAC, building envelope, industrial systems, and a couple of the shorter chapters behind us, we now turn our attention to the indoor air quality. You may wonder why we're discussing indoor air quality. This is Energy Systems Engineering, and how does indoor air quality affect those energy systems? And we'll get to that at the end of this slide. To begin, our definition is that air in which there are no known contaminants at harmful concentrations as determined by cognizant authorities, and with which a substantial majority, 80% or more, of the people exposed to do not express dissatisfaction. We will consider that good air quality. So we're looking at contaminants at levels expressed by authorities, in addition to 80% or more of the people who are exposed to don't express dissatisfaction. The balance of this brief course, this brief chapter, focuses on fundamentals of indoor air quality and indoor air quality control. But let's get back to the question that I asked originally. Why? Why are we discussing indoor air quality? And that's because the balance of air quality and energy management. Air quality itself is not an energy management topic, but changing air quality is. As we consider indoor air quality, there is first the fundamentals of indoor air quality. Where does air quality and poor air quality come from? And what do we need to consider when we consider improving indoor air quality? And what we say is indoor air quality is the 3 P's: people, pathways, and pollutants. People are subjective indoor air quality monitors that they don't feel parts per million, or they don't measure parts per million, but rather they just tell you how they feel. In addition, their feedback and limits, they can't be controlled. People file lawsuits, and therefore their feedback needs to be quickly investigated. You can't ignore the, quotes, bad apple. So people affect the indoor air quality and the perception of indoor air quality. And pathways. Pathways are any route for a contaminant, including the air conditioning system. From an indoor air quality perspective, the air conditioning system can be a cure, but can also be the cause of poor indoor air quality. Some typical pathway considerations are ventilation. Obviously, we need fresh air. Another one is temperature, because temperature increases the perceptibility of contaminants. Not necessarily itself an indoor air quality issue, but it has an effect on your perception of indoor air quality. And humidity. Humidity also not an indoor air quality issue, but high humidity can result in mold growth, which can be very hazardous. And filtration. ASHRAE recommends, we'll see filtration a little bit later, a minimum MERV, a measurement of efficiency and filtration, of 6. That's not very good. And airspeed, like temperature, the airflow, the airspeed, can change the perceptibility of air quality, although it in itself is not an air quality issue. Fresh air intake. If you have the location of your fresh air intake in the wrong place, it can have a dramatic effect on indoor air quality. Consider vehicle exhaust, trash bin odors, cooling towers, and also consider the minimum code may not always be sufficient. Just because you can measure that your intake is the required feet away from something, if you're still perceiving poor air quality, well, that is a bigger concern than the fact that you've met the code. The third fundamental of IAQ is pollutants. The types we'll discuss here shortly, but the source of any of these types, the source of any of these pollutants could be indoors or outdoors. So what are the types? First is particulates. Airborne particulates are classified as something called an aerosol and can range from the size of a human hair at 100 microns to an asbestos fiber, picture here on the lower right, of less than half a micron. So particulate size varies dramatically. Next are bioaerosols. As you might guess, these are biological aerosols, biological airborne particles, viruses, bacteria, mold, pollen. Another pollutant is gas and vapor, ozone, radon, carbon monoxide, carbon dioxide, volatile organic compounds, so-called VOCs. When you're considering controlling indoor air quality, the best thing is to remove the source. Whatever's causing the air quality problem, take it away. If you can't take it away, filtration works, but it doesn't work on gases. Certainly gas filtration is available. If you have a problem with VOCs or with carbon monoxide, gas filtration is possible, but it's just not cost effective in a large-scale commercial building. The last resort for indoor air quality control is dilution, bringing in more good quality air. We said earlier we would discuss filtration, specifically this concept, this measurement of air filtration efficiency known as MERV. And the ASHRAE requirement is a MERV of 6. It's not even on this chart. A MERV of 6 means that it's efficient in particles that are larger than 100 microns. As you look at this list of what might cause you a perception of poor indoor air quality, burning wood, tobacco smoke, smog, you see that having a filter with an efficiency of 11 or higher is a minimum if you want to be able to filter out that size particle. Now, for example, smog, you'll filter out the particles in smog, but you won't filter out the gases, carbon monoxide, carbon dioxide. Those are odorless gases. And to summarize this short topic, this indoor air quality chapter, we're going to bring back why do we bring it up in the first place. Rather than it being very short, we could have just left it out. But we left it in for this slide. We left it in because when you pursue an ECM, an energy conservation measure, there can be indoor air quality consequences. So we bring up indoor air quality because of its interplay with energy conservation measures. So what are they? The first is, if you eliminate leaks in your building or you purposefully reduce outside air makeup in order to get efficiency out of your HVAC system, the indoor air quality consequence is that you will reduce fresh air. You need to be aware of that. Next is maybe you performed an exterior wall modification for insulation or for a vapor barrier. Well, maybe you interrupted water drainage that was there, that would have occurred before the exterior wall modification. And now the water has nowhere to go, and you could have mold growth. Maybe you used one of the chilled water reset or supply air reset control strategies we discussed during building automation and control. One of the consequences there for indoor air quality can be increased humidity. The dew point of the air has to be such, and the temperature of the water in the coil has to be such that condensation occurs for the humidity to come out of the air. If the water pipe's not cold enough, you may not get the humidity reduction you're used to. You can also have surface condensation on cold things that you didn't used to have because you now have more humidity. And of course, with increased humidity comes increased likelihood of mold. Maybe you changed the filter type because you wanted to improve HVAC efficiency. So you took a high efficiency filter out, put a lower efficiency filter in because it causes your fans and your HVAC system to run more efficiently. Well, you must be aware that if you drop that rating too low, you have an increased particulate and mold growth from biologicals. And last on this list is maybe you reduced light levels. Maybe you found that your illumination was higher than it needed to be, so you delamped to bring light levels down. Well, this is a subjective measure, but you do indeed, when the space is darker, it will reduce occupant tolerance to indoor air quality. The same people that didn't say anything yesterday, when the space is a little darker, they may smell that. They may sense that. They may feel a less tolerance for an adaptation in indoor air quality.